Hello and welcome to the Terran Space Academy. This is Rocket Science, and today we will be looking at several recent developments in the space industry. I don't say a lot about Starship modifications and updates until they fly. There are several reasons for that. One is that these are covered in depth by other presenters, and I don't think I would be contributing much by rehashing them. And while I don't necessarily need to see every piece of angle iron moved at Starbase, I do watch these myself to keep up with what's going on. My favorite is CSI Starbase, because they provide the most in-depth technical analysis that I've found. My goal with these lessons is to make sure that we have a broad understanding of the fundamentals of spaceflight and spacecraft construction. Whether you plan to or are currently working in the aerospace industry, or just love space and want to stay current on the science, we are here for you. In this lesson, let's catch up on recent developments and look ahead to the future. As everyone starts going crazy over putting AI into mobile robotic bodies, it's important to remember that almost everything we need to do in low Earth orbit or on the moon can be done by telepresence. The bandwidth of data transfer determines whether you get continuous high-resolution 8K video or simple black and white images, like those used in the 70s to operate the lunar rover. NASA is an amazing organization that has done much for humanity in space science. That being said, there are some very glaring failures, besides the obvious. One of the greatest failings of NASA so far is that it has not sent rovers, telescopes, and construction equipment to the moon to be remotely operated. Both the Americans and the Soviets had the technology back in the 1960s to do this, and neither side did. The U.S. sent a few probes and orbiters, and then 6 human missions, which accomplished an amazing amount of science in their short time. The Soviets sent probes, orbiters, landers, and rovers. And while they gave up on landing a person on the moon, they did have several teleoperated rovers that explored the lunar surface, driven by technicians back home. And some of these returned samples. Russia inherited the Soviet Union's credit for its space successes, but has abjectly failed to do anything at all original. Even managing to crash the Luna 25 lander in 2023. The exact model that the Soviets had successfully landed more than half a century before. And since 1972, with the exception of a few orbiters, NASA has also failed to explore the moon further. Now you all know that Chang'e 6 successfully landed on the moon's far side with communications help from a relay satellite in an L2 halo orbit, and sent back the first samples from this side of that desolate world. Chang'e 5 had returned samples from the near side, and the Chang'e 6 mission was very similar, with a lander, rover, and return rocket. The mission lasted 53 days, culminating with a lunar launch, transfer, and return scenario that was a close copy of the manned Apollo missions. Anyone who does not realize that this is practice for an Apollo-like landing is ignoring reality. On its return to Earth, the capsule landed on the desert plains of Inner Mongolia, and the samples were airlifted to Beijing, where scientists will evaluate them and inform the world. Maybe. If they find something revolutionary, it might end up classified, behind China's new Great Wall, which is why we need equipment up there of our own. The ability to teleoperate rovers and robots on the moon in real time makes it exponentially easier than operating equipment on Mars. Artificial intelligence has not progressed to where we can land truly autonomous machines, but those days are coming sooner than most want to admit. While I love the idea of colonizing space with humans, and believe that anyone over the age of 50 should be able to take any calculated risk they choose, including a one-way trip to the Red Planet, I have no problem with AI, robotic, and teleoperated equipment being used to build habitats and industrial facilities on the moon. This actually makes a lot more sense. Human beings are fragile, and we break down in a low-gravity, high-radiation environment. While the maximum radiation exposure to be expected on Earth is at most 2 millisieverts, exposure in a suit and unshielded habitat on Mars will average over 100 times that. about 250 millisieverts. As a general rule of thumb, memorize these numbers. Less than 1 millisievert on Earth average, about 250 on Mars, about 500 on the Moon, and about 750 in open space above the Earth's magnetic shield. This is much too dangerous to send young people into, but would be fine for people over 50, as they have many fewer rapidly dividing cells, and any increased risk of cancer will fail to get us on average before time does. Another frustration I have with NASA is underutilization of the Falcon Heavy rocket. This machine just launched the Hugo satellite into orbit. A Falcon Heavy launch in fully expendable mode would cost $150 million and could get 63.8 metric tons to low Earth orbit, or 16.8 metric tons into a trans-lunar injection orbit or a Mars transfer orbit. And while we've landed multiple rovers on Mars, America has not sent a single one of them to the moon, though a few private companies have tried. And of course, China is rapidly surpassing the rest of the world in lunar mission operations. The Soviets used solar panels to run their rovers during the lunar day, and radioactive decay to keep them warm during the long lunar night, in the early 70s. With new advancements in thermovoltaics, which turn infrared photons directly into electricity, we could use the exact same technology to operate a rover through light and dark on the moon today. So why don't we design an 18.5 metric ton robotic lunar lander and rover system? When it comes to getting into orbit, I usually like to use the number 9,400 meters per second for the delta V needed to overcome atmospheric and gravity drag, and to get to a minimal low Earth orbit. But we already said that the Falcon Heavy can get 18.5 metric tons to a lunar transfer orbit. That puts us about here on our delta V map. That leaves us needing 145 meters per second delta V for lunar orbit insertion or capture, about 68 meters per second to get to a low lunar orbit of 100 kilometers to look for a good landing spot, and 1,721 meters per second to get down to the surface. This gives us a total of 1,934, which I usually round to 2,000 for a little safety margin. If we start with a maximum mass of 18,500 kilograms in a lunar transfer orbit, and use our delta V equation, modified to solve for final mass, we can calculate our landed mass. But in the equation, we need to know the exhaust velocity of the rocket engine we are using. This is predetermined by the propellants we choose and the nozzle. If we go hypergolic with MMH and NTO, that would be about 325 seconds of specific impulse, times 9.81 meters per second squared for an exhaust velocity of 3,188 meters per second. We see that we will touch down on the moon with a mass of about 10 metric tons. If we use the more efficient hydrogen-fueled RL-10 engines, we could bump that up to a little over 12 metric tons, a difference of about 4,400 pounds. That's a big difference, a 20% increase in landed mass, in fact. But cryogenic hydrogen fuel has a very low density and is very hard to work with, and one of the shortcomings of the Falcon Heavy is its relatively small fairing. So if we compromise and go with a methane-fueled lunar lander, like the intuitive machine's Odyssey, we can get a little more than 11 metric tons on the surface. This is a very nice compromise, since cryogenic methane fuel is much denser than hydrogen, up to 450 kilograms per cubic meter versus 71, which is not as dense as the monomethyl hypergolic fuel at 870 kilograms per cubic meter, but non-toxic with higher efficiency. If we look at a Falcon Heavy rocket fairing, we see that it has a volume of about 260 cubic meters or 1,435 cubic feet. The intuitive lander is the pathfinder for our mission, having been the first methane-powered spacecraft to fly on an operational mission. It used the VR3500 engine built by Boeing. I know what you're thinking, but Boeing engineers are just as smart as those anywhere else. It's management and corporate culture that's the problem there. The VR3500 had a thrust of 3,500 newtons. So quickly do some rough math in your head and calculate that it could hover a little more than 350 kilograms against Earth gravity, but a lot more against the moon's 1/6 Earth normal gravity. So multiply that number by 6 and get about 2,100 kilograms. If we are going to land with 11,000 kilograms, and we want to hover before landing, we will need about 6 of these to be safe. But I wouldn't use this engine. It only has a specific impulse of about 350 seconds. Probably because of the limited size of the nozzle. In space, you need an infinitely long nozzle to maximize efficiency. That's impossible with a bell nozzle, but accomplished with an Aerospike. We are going to use the 20,000 Newton methane-powered Aerospike engine already built and tested by Pangaea Aerospace. This would let us hover up to 2 tons on Earth and 12 on the Moon. Are we in the ballpark? Let's look back at Apollo. The Apollo Lunar Lander had a launch mass of 15,200 kilograms, with about 8,200 kilograms of propellant in the descent module, with a specific impulse of 311 seconds, burning Aerozine 50 and nitrogen tetroxide through a TRW-built engine. It produced a total of about 2,500 seconds of delta V. The percentage of propellant mass to launch mass was about 54%, so we should be close. The oxidizer to fuel ratio of liquid oxygen to methane is about 3.7 to 1, meaning we will need 3.7 kilograms of oxygen for every 1 kilogram of methane. Liquid oxygen has a density of about 1,250 kilograms per cubic meter, and liquid methane, we said, was up to 450 kilograms per cubic meter. We had calculated that we would need almost 7,500 kilograms of propellant for our model. Now the difference by mass is 3.7 to 1, so 79% to 21%, but the difference by volume is 57% to 43% because of the different densities of these cryogenic propellants. The Falcon Heavy fairing has a diameter of 5.2 meters, wider than the 3.7 meter Falcon boosters in second stage. With a height of 13.1 meters, if it was a cylinder, it would have a volume of pi times r squared times the height, so 278 cubic meters. That's more than twice the volume of a standard cargo trailer on an 18-wheeler. But not all of the volume inside is usable due to the conic shape of the top, the attachment platform, and the safety margins on the sides. There's a Falcon Heavy user's manual available from SpaceX, and here's a picture showing the useful payload volume compared to the fairing itself. It looks to me like the payload volume is not as wide as the second stage here, so let's go from 3.7 to 3.5 meters in diameter, and it's less than half as tall, so let's say 6 meters. Using these, we get a volume of 58 cubic meters, so let's go with 60. So about 1/5 of the payload volume for our lander would be propellant. Now what would I land on the Moon? I've said before that I would land a regolith sifting rover that would scoop up the lunar dust, sift out all the big pieces, and load the fine dust into a 3D printer on the lander. These would be 3D printed into the first coins on the Moon. We'll call them a lunar. We'll load these on a lunar return vehicle and send them back to Earth. Each will have its own serial number, and we'll auction them off to fund our next project. Unlike the lunar materials returned by the Apollo missions, the Artemis Accords say that we own what we mine and return. Something to think about. I've also thought that if I was designing a spaceship right now, I might make it look like this one, being planned by Intuitive Machines, and I would make it exactly the size of a current Starship Heavy fairing, but allow it to expand once in orbit with an inflatable middle habitat section, taking advantage of all the available volume, without changing flight characteristics. That way we could have 63.8 tons worth of propulsion, supplies, and propellant on board for a long-range mission to Mars. Let us know what you would make. A few lessons ago, I suggested we look at a Raptor 9, so we don't waste all of those Raptor 2 rocket engines that have been made. This rocket would have 9 230-ton force engines on the first stage, meaning it could hover around 2,070 metric tons, or launch about 1,400 metric tons, with a thruster-weight ratio of just a little less than 1.5. We'll put 3 engines on the second stage and 1 engine on the third stage. Here's how I did mine. I chose to look at a mass to LEO of 100 metric tons to start. Our goal is at least 9,300 meters per second of delta V, but I would prefer 9,400 to be safe. I subtract the payload mass from the total mass and calculate my dry mass and propellant mass from that new number. I chose an estimated total dry mass of 10% of the total mass, which is pretty close to what you will find in many rockets. I then assigned 60% of the mass to the first stage, 25% to the second, and 15% to the third. You can do it differently. Next, I subtracted the calculated dry mass from the stage's total mass and got the propellant mass for each stage, which gives me the total down here. Then I calculated the first burnout mass by subtracting the propellant mass for stage 1 from the total mass at launch, and using the rocket equation to get the delta V for this stage. I then do the same for the other stages, and I see that we don't get our needed delta V. So I drop the payload mass by 25% and let the spreadsheet update, and we still don't make it. So we try to get the same mass to LEO as the Falcon Heavy, and we fail. In fact, I must drop to 60 metric tons to get close enough. SpaceX already has a rocket capable of exceeding that, so this is probably not a good use of our Raptor engines. So, for our next exercise, let's go back to the amazing single-stage-to-orbit Chrysler Serve. Watch this lesson if you haven't. Let's make a big methane-fueled version using 100 Raptor 2s around the perimeter. How much could we get to low Earth orbit? Let me know what you find out. Stay connected, and a special thanks to our new and recently promoted Patreon supporters. I've reloaded the current officers roster, and let us know if there are any mistakes. We appreciate you. Thanks for listening, and stay safe. Ad Astra Pro Terra.